In the last video, we talked about, basically all the aspects about simple harmonic oscillation, including its kinematics, its activity-AD relationship. We also studied its force and its energy. So today, I'm not going to introduce any new, more fancy concept because there's none. I just want to talk about some different kind of simple harmonic oscillation and how to find out the frequency to this. Okay. So usually whenever we see a simple harmonic oscillation, we want to characterize its frequency, because frequency will really tell you it's like the characteristic features for a simple harmonic oscillation. So for example, if you have a molecule vibrate, we will say, okay, this molecule will vibrate at very special frequency, and you can use the frequency spectrum to figure out what molecule it is. Okay. We will talk more about this in next semester. But here I just want to tell you how to think about frequency in a simple harmonic oscillation. Okay. So since frequency is like every simple harmonic oscillation, they all have their special frequency. That special frequency is completely depending on the system itself and also the details of that systems. So for example, pendulum is a simple harmonic oscillation. So why is a pendulum a simple harmonic oscillation? To answer that question, let's try to build a model about it. This is a pendulum, and as we see in the demo, that this pendulum, the ball here, will go back and forth. So it's like it's doing a simple harmonic oscillation in the x direction and almost not moving in the y. Okay. I know there's a little bit curve, but let's say we focus on very small angle, then simple harmonic oscillation will be just appear in x direction. Okay. So to prove that this is a simple harmonic oscillation, we need to come back to the definition of simple harmonic oscillation. The definition of a simple harmonic oscillation is that the force, like when I move this object away from equilibrium point, it will experience a force, and such force is proportional to negative times the displacement. This means the oscillation, like restoring force, and this means the simplicity because it's linear. So which means a pendulum also feel this guy, when I pull this guy over, it will also feel a force to pull it backward, negative, and that force will be proportional to this displacement, this delta x. So let's take a look and see whether this is true in this case. So first, I'm gonna draw the free body diagram because now I wanna analyze the force. I'm gonna draw the free body diagram here. So my ball will feel a tension going this way and feel a gravitational force this way. And if that is the angle here is theta, then this angle here will be theta as well. So I'm gonna label theta here. So now let's split this system into x and y direction. That's x and that's y. So you can see that in the x direction, this guy is doing like a back and forth. It's doing like this oscillating behavior. So we observe an oscillating behavior. So F equals to MA, where A will be changing all the time because it's oscillating. And in the y component, if the angles are small enough, then this guy's almost not moving in the y direction. So in y component, it's not moving. So Fy is MA, Fy is MA, which is 0. So what's the Fx in this case? Fx here, you can see here tension and gravity. Gravity has no x component, tension has a little bit apart. So this tension can be split into x direction and the y direction. Okay. And in the x component, we only have a tx component. We only have the tx part. So Fx here would be negative times tension, like times tension times x equals to MA, which is, I'm gonna write it this way so it will be more clear. So Fx here is provided by part of the x component of the tension, so which is Tx, negative Tx equals to negative T sine theta, because Tx is the opposite of this angle. Now let's come back to look at y component. The net force in y component is 0, so which means the Ty and the gravitational force will cancel out. Ty is T cosine theta, Fg is mg. Okay. So now we have like two information. But none of these forces looks like, but this force is the Fx here. It doesn't look like anything like this, right? Except that there's a restoring force, which probably match up. So let's massage this equation a little bit and see whether this force is indeed providing a simple harmonic oscillation. So let's massage it more from here. We know it's negative T sine theta. Okay. So what is T? From here, we know T is mg over cosine theta. So that I'm gonna replace my T with the cosine theta here. All right, so here I'm gonna do an approximation. Assuming that I only care about this pendulum at a very small angle, and when I say small angle, I mean an angle which is less than, I don't know, 1 degree or 5 degrees. Okay. 5 degrees. Some people use 10 degrees. I usually do 5 degrees, but basically what I mean here is it's a very, very small angle. When it's a very small angle, okay, so think about it, like when it is a very, very small angle, you can see that hypotenuse and the adjacent are almost the same. So when you do cosine theta, it will be the same number divided by almost another same number. So that will give you 1. So cosine theta is almost to 1. And on the other hand, sine theta is the adjacent, it's the opposite over hypotenuse, right? So you can, when it is really, really small, you can look at this triangle as if it's a sector. Okay. So this length is almost the same as, you know, the radius times the theta. Okay. So when I do opposite over hypotenuse, I get theta. So at small angle, sine theta is almost the same as theta. Now I'm gonna plug this approximation back into my Fx and see what I get. So my Fx, here will be negative mg. Cosine theta is 1, so I can ignore that. Sine theta is theta. So now you can see it's very close to this format, right? Okay. So what's the relationship between theta and the delta x? Okay. So as we said, if the angle is really, really small, such a triangle can be viewed as a sector where this is L, this is theta, and this delta x, this part, it will be the radius times the angle. So theta here will be delta x over L. If I plug this back in, I'll get this. Times delta X. All right, so now you can see in X direction under this approximation, it is indeed a simple harmonic oscillation because my force in X direction is proportional to negative and times the change in negative times the displacement. So you see, this tells me the system is indeed a simple harmonic oscillation. All right. And this not only tell me the simple harmonic oscillation behavior, it also tell me, this guy also tell me the frequency of the system. Okay, so how so? Okay, I'm gonna erase this part. Okay. Remember that remember that in the spring that if F equals to negative Kx, and then if F equals to negative Kx, then the system, the frequency of the system, how do I put this? Remember in the last video what derived that in the spring system, F equals to negative Kx. And because this equals to that and also equals to MA, then we can derive that the frequency of the spring is the square root of K over M. So it's the same idea here. We can also set this equals to MA, and this will behave like K. So the frequency, that's a spring. So the frequency for pendulum will be very similar. It will also be omega equals to K over M, but here my K is a lot more complicated, it's mg over L divided by M. So this canceled out, and then you get square root of G over L. This is the most important result that I want you to learn in this video. So you see, remember that if you're doing the lab in the beginning of the semester, that you want to study the period and how's the period related to, to all the physics quantities. And then I believe that most of you discovered that, oh, the period, which is related to the frequency, it is related to the length of the pendulum and not the mass. And if you look at it in this equation, that's exactly what this equation is telling you. It's related to the length. If the length is longer, then the frequency will be lower. So it takes more time to do one cycle, okay, to do one swing. But I can see the frequency of the pendulum, the angular frequency of the pendulum, has nothing to do with the mass. So no matter this is a small object or it's a very heavy object, they will both swing at the same frequency as long as the length of the pendulum is the same. But remember, this is a very important result, but this result is coming from an approximation. So probably in the lab, you hear that, you heard that your lab TA told you that, oh, try to do the small angle instead of the large angle. Because this kind of simple harmonic oscillation, it only happens when you have small angle. When you have a large angle, the frequency will be a lot more complicated. It actually depends on the angle, but it's a very complicated dependence. Okay, so I'm gonna conclude our finding here. So how do we calculate the angular frequency of any simple harmonic oscillation? Now we know the spring, the frequency of the spring depending on the mass of the object and the spring constant. So omega is square root of K over M. The frequency also depends So a pendulum is also spin harmonic oscillation, and its frequency only depends on the gravity and also the length of the pendulum. There are a lot more complicated simple harmonic oscillations, such as maybe I have an object, with two springs hanging them. Maybe they're hanging in parallel, or maybe these two springs are hanging in series. So this figure means there's one spring here and another spring attached to it. Or you can have like carbon dioxide, where you have spring on both sides and vibrate in and out with respect to this carbon atoms. So they all have their special frequency dependence. And the way to find out this omega is pretty much the same logic. You want to find out what's the effective K in this case. What's the effective K here? What's this constant? What's this constant in all of these cases? And then you can use the spring, like you can start from spring, and to help you find out the frequency dependence for specific this case. So I'm gonna give you two examples here, and then you will think about this example in the discussion. All right. So first, this is the springs in parallel. Okay. So you see this guy, if we draw the free body diagram of this guy, it's gonna feel a spring force pulling this way from the first spring, and you will feel another spring force pulling back in the same direction. So the net force would be negative K delta X minus K delta X, because they are all, it's all both, both of them are pulling backward. So my F net is this. So again, whenever you see F equals to negative times delta X, it means this system is a simple harmonic, it's doing a simple harmonic oscillation, where this guy is the constant. So the frequency of this system would be omega equals to square root of K over M, while here my effective K is 2K in this case. So the spring, this system, its frequency is related to, is square root of 2K over M here. Okay. So now you can see, so this means my frequency, like compared to only one spring system, you can see this guy has a higher frequency than this guy, okay, because it has a square root of 2 here. So this one will actually spring faster than this guy. Now let's take a look at another case, which is the two springs are connected in series. So here's a spring K1, spring K2. And if I look at the object, this object will be stretched out by delta K, by delta X. And if I want to find out, so say this is SHO, and I want to find out the frequency of this, like the frequency of the system. Okay. So to find out frequency, remember like how we did it before, is that we're trying to figure out like what's the force acting on this object. And if it's a simple harmonic oscillation, then this net force will definitely be proportional to negative delta X with some coefficient here. And with this coefficient, we can use this coefficient to find out my frequency. So I'm gonna do that here. If I draw the free body diagram in the system, you will see this guy only feel a force, which is the spring force coming from the second spring. Okay, which is the spring force of the second spring is equal to negative K2 times delta X2. All right, but this delta X2 and this delta X are different things. The delta X2 is the displacement, like the stretch, like the length change of the second spring. Delta X is This guy is the length change of the second spring, and the second spring only. But the delta x here, we want to figure out is a total, like is the displacement for both for the total system. So this delta x is actually the change in of the second spring plus the change in the first spring. So I'm gonna start from here, but I have some trouble because when I look at my force acting on the system, it is this instead of, you know, this. Okay. And my goal is to massage my force into a format like this so that I can tell my effective spring constant. But now from physics, I only know that this guy is proportional to, the spring force is negative, K2 times delta X2. So I need to do a little bit work to convert my delta X2 to delta X. And this is how I'm gonna do it. You don't need to memorize like all the derivations style. I just want you to sort of follow the logic and know the final result. So to do that, I need to sort out what's the relationship between delta x and delta x2. So first, I know delta x is nothing but delta x1 plus delta x2, because the total stretchness will be the stretchness of the K1 and the stretch from the second spring. And we also know another information is that if you look at the system, if you look at the particle here and draw the free body diagram, this particle will feel a spring force to the right because it's pulled by the second spring, and also the spring force to the left because it's pulled by the first spring. And these two forces should be the same because the item in the middle is not moving. So now that we know F1 equals to F2, okay. And the spring force 1 is nothing but K1 times delta X1. Spring force 2 is K2 times delta X2. I cancel out all the negative, so don't worry about it. And then you can see, now I can rewrite my delta X1 to be in terms of delta X2 times something else, and then plug this back into this equation to get this. Okay. And now I'm gonna sort it out. So I get K2 plus K1 over K1 times, so I'm gonna factor out the delta X2 and then divided this on both sides. So if I do that, I will get delta X2 to be this guy times this guy. If you want to follow the steps, I would recommend you to pause the video and try to carry out the math by yourself, so that will give you more intuition. So now I successfully rewrite my delta X2 in terms of delta X, which is exactly what I want to do here. So I'm going to plug this whole thing here. Okay. Okay. I'm gonna erase, this is my goal, and I'm gonna slowly migrate to my goal. Now I know my delta X2 is nothing but this guy. Times delta X. Then that means this whole thing, this giant stuff, is my effective, K, right? Okay. All right. So I'm gonna jump to the next page. So now we figure that this whole thing, this big thing, is my effective K. And then I know my frequency for the spring is the effective K over the M. So I can just plug this whole thing into my effective K and times 1 over M here. So this is the frequency when I have two springs in series. All right. So that's the idea about like how to find the frequencies for like more complicated system. Here, I want you to pay attention to sort of the result and also the logic behind that, you know, like how to find effective K and how to use that to decipher, you know, the information, like what's the frequency depend, like how does the frequency depend on the other physics variables. All right, so that's it. And